All right. So let me tell you how to never make mistakes, and whoever's late just doesn't get to make mistakes. You do this. Well, computers used to make mistakes, and it was a real problem. So in the 70s, the computer was becoming a useful tool, but they made so many mistakes that well, let's say I say the main law mistake. Let's say that 1 in 1,000 computations or 1 in 10,000 computations was wrong. Well, banks wanted to buy these computers to keep track of their books, but the problem is 1 in every 10,000 computations was wrong. And when you're talking about large sums of money, right, this is not acceptable. It's not acceptable to be wrong every once in a while. And so there was a company, I think called Tandem Computers or something like that, and they made millions because they invented the first computer that doesn't make mistakes. Not bad, right? And it's actually a very simple idea. So the way computers don't make mistakes is that they check as they go. So when you ask a computer what 8 times 5 is, it doesn't just say 40. It does it multiple times, and if it gets 49, at least 9 out of 10 times, it figures 40 is probably correct. All right? And so it's called checking as you go. So let's say that you have to do a computation. And by the way, here's an interesting question for all of you, and this is actually a pretty interesting question. If I gave you let's say some billionaire walks into the room, and they have a worksheet with 100 of these 2-digit by 2-digit multiplications. And they're like, okay, they start handing them out, and they say, look, everyone who can do all 100 of them without making a single mistake gets $1 million. Okay, which of y'all are getting paid, and which of y'all are not getting paid? Okay, yeah?
I think I can do 102 by 2 multiplications.
What's that?
How much time do you have?
Unlimited time.
I'm getting that mill.
You're getting that bill?
I'm getting the mill.
Okay. So the sad reality is some of you are not getting paid. That's the sad reality, right? Okay. Here's another question. Suppose you had a calculator, and that calculator, when you typed in calculations like that, it gave you the correct answer, let's say 99% of the time. What would you do with that calculator?
Well, you check yourself.
I would do every problem twice.
Yeah, actually you could. Well, probably even more than twice if you really want to be sure, right? But actually the first thing I would do is just throw the calculator away. Trash can, right? Okay, that's what you said, okay. Because, I mean, who really has a use for a calculator that might not even give you the right answer, right? There are other calculators that will give you the right answer, right? So why even mess around with it, right? That calculator is worth negative value, right? Okay, now suppose you're in charge of a company and you have an employee who gets the correct answer 99% of the time. What would you do with that employee?
Fire them.
I'm kind of leading y'all in that direction. Now, I don't know if you actually fire them or not, right? But the point is, y'all see that there's value in not making a mistake. There's a lot of value, okay? Let's say you're designing bridges, and then you're in charge of designing the bridge, and then the bridge gets constructed, and then on the 5th day operation it collapses and hundreds of people die, right? And then you're like, oh shoot, forgot to carry the one. Not acceptable, right? And you'd be like, well, I did everything right. It was a beautiful bridge. Oh, except for that one thing, right? No, not acceptable, right? So when I want to raise y'all's standards, right? From childhood to adulthood, to irresponsible to responsible, right? That's what we're kind of talking about here, right? You can't expect someone to pay you money to do stuff if you're getting the wrong answer all the time, right? Any of the time, it's not good, right? Trying to raise your standards here, right? Now, guess what? We're all human beings. You guys have seen me make mistakes already, right? You're going to see me make more mistakes. I'm rushing. I'm going way too fast. I got a time pressure. But in my own calculations, the point is it's unlimited time. I'm not going to be publishing papers that have mistakes in them. I'm not going to be giving presentations, that have mistakes in them, things like this, okay? This is where you have to have, like, a standard. So how do you not make mistakes here? Well, you check as you go. So here's the rookie mistake is you do the whole computation, and then you do the whole computation again, and then you do the whole computation again. That's the rookie mistake. What you want to do is check as you go. So what does that mean? Let's say there's 10, 3, 4, 5, 6, 7, 8, 9, 10. Let's say there's 10 steps to do a computation like this. And let's suppose each time you do a calculation, let's say let's say there's a tenth of a chance you make a mistake. Right? Now that's not too good, right? But nevertheless, this is very much a human being, right? Well, actually, it's probably more like a hundredth of a chance, right? Let's say there's 1% chance. That's probably closer to reality, right? Okay, so you do 8 times 5, you get 40, right? You're going to get that at least 99 times out of 100, right? The trick is you check that computation 3 times. Right now, there's 1 chance in a million that you've made that wrong, right? And then now you have 10 of these computations added up. And then you have 10 chances in 10 million that you got the answer wrong. So now there's only 1 chance in 100,000 you're going to mess up this computation if you check as you go. Do you all guys follow the math? This is how you do it. You check as you go. What you don't do is 1% chance, 1%, do it 10 times. There's a 10% chance this is wrong. Then you do it the whole thing all over again, right? And then the whole thing all over again. You get 1/10, 1/10, 1/10. It's only 1 chance in 1,000. Actually, you can see how the numbers don't favor you, right? It's harder to catch the error if you do the whole computation. Also, look, as a math physics double major myself when I was an undergrad, of course I learned this lesson the hard way, and trust me, you can spend hours looking for that mistake in the middle, and then you find out actually you had 3 mistakes in a 5-page computation, right? This should never happen. Any of y'all computer programmers? You check as you go, you compile as you go, you make sure it still works, right? I mean, this is how you don't make mistakes. So that's the theory. Good luck with the practice. Wish you all the best on that. It's a skill. How about we agree? I told you something. You probably like, yeah, of course, right? But I mean, it's something you want to think about and practice, for sure.
What about efficiency? Like, when you consider how much time you're going to spend?
Life is mostly an open book test. It turns out for most things in your life, time is not a major factor. Now you might say, well, how come we have time tests then? And practicalities of life, right? Time tests, I'm not so sure. I mean, they test something, right? But I don't like it. Do you guys like it? Does it seem like life is mostly an open book test, right? You build the bridge, it's due, I mean, look, you've got months, years to build the bridge, right? So, you can work overtime. There's no point when someone says pencils down, right? Like so this is take the extra time, right? I say this from experience as well. I know there's a number of y'all are physics majors. For the math majors, homework is interesting. It requires creativity, but the computations don't seem to get that long to me. If you're a physics major, it gets out of hand pretty quickly. Right? Physics computations seem like they could go on just for pages, after page after page after page. And trust me, if you want, you're talking about efficiency. If you want to do a long computation quickly, go slow. All right? You can quote me on that. If you want to do a long computation quickly, go slow. Now, if you want to spend the rest of your life and still get the wrong answer on it, yeah, go fast. Just go ahead and just whiz through that, right? 50-50, you get the wrong answer at the end of it, right? And then you want to spend the rest of your life actually checking it, trying to figure out where you made that mistake, right? I'll tell you what, truth of the matter is, you're better if you just throw that in the trash can and start over. Anybody have that experience? Yep. I mean, I'm not joking around here. You literally, you show me, when students come up to me with physics homework especially, I used to help people with their homework a lot as a student. And if someone says, hey, can you help me figure out where I made my mistake in this calculation, right? No, I can't. This is way too hard, right? I'll start from scratch and we can work the problem together from scratch, right? But, so you can't make mistakes, right? Now, let me tell you one of the coolest things I ever heard someone say. This is a nerd cool, okay? I had a friend, and he was a fellow math physics double major, and we were in a math class, and we were both taking little notes, right? By the way, I don't think you have to take a lot of notes. Just you jot down whatever you want, but note taking can be overrated because it's better to listen and understand. Like that's step 1. Step 2, if you want to write something down, fine, right? But if you ever have a choice in a math class between really understanding or writing down everything the professor says, I would say really understand. But anyway, we're sitting there, and I noticed that maybe we were turning in homework. And I noticed he was turning his homework, and his homework was in pen, right? And mine was in pencil. And I noticed he had a pen, and he was taking notes with a pen, and I was asking him, why do you use a pen? Why don't you use a pencil? I mean, what do you do when you make a mistake? And he said, I don't make mistakes. Which I was like, oh, okay, that's so cool, all right? And then I was like, yeah, I'm going to do that too. And ever since then, I've been using a pen. Right? And it gets your brain in the right frame of mind, which is, if you're not sure if it's right, you don't write it down. Right? I mean, you check as you go. It really gets a mental discipline. Right? You don't write now. I still make mistakes, okay? But you scratch it out a little bit, right? But the point is, like, you have to scold yourself mentally when you do make a mistake. It's a frame of mind. Okay. Anyway, you'll see what I'm talking about. The more you can go 3 times slower and don't make mistakes, and that actually is faster at the end of the day. Okay. And then when of course, efficiency is an issue when you're teaching a class like I am right now, and you may find other situations too, and you just have to optimize. Okay, so we were talking about dot products and cross products, and then we'll get to the Frenet formulas here in just a second. Are you all doing the Frenet formulas in your homework right now? Okay, homework due Friday. So I explained last time about the dot product, and so dot product. If you really want to disappoint me, take the dot product of 2 vectors and then get a vector out. Okay, the dot product of 2 vectors is a number. It's Vx Wx plus, not comma, Vy Wy plus Vz Wz, right? And so that's a number. It's pluses there, not commas. If you put commas, then I'll really, it's be clear to me that you have no concept what the dot product is, right? Dot product is a number. And in particular, it has some nice properties. It's bilinear, okay? And just to make sure everyone understands what I'm talking about, it means that if you have, 3 vectors, you have a distributive law, right? And the fact that you have the distributive law is one side of saying it's linear. Here in the second slot, we also could do u dot 5 v, and this is equal to the 5 factors out, right? Times u dot v. Okay, so when you have these 2 properties together, we call this is the linearity property in the second slot, but we also have this linearity property in the first slot, and so therefore, since it's linear in both the first and second slots, we call it bilinear. Okay? Does everybody make sense what bilinearity is? It's just what multiplication has, and when your regular multiplication with real numbers has, but it's also what the dot product has, which I'm representing by this sort of thick dot. And then key properties of the dot product is, u dot product v is equal to the length of v times the cosine of the angle between them. And I proved this last time using the fact that u dot u is equal to the length of u squared. Okay, so really, if you're like, where did that definition come from? This is really the first thing. Is you look at the rule of Pythagoras in 3 dimensions, and then you realize the length of a vector squared is u dot u if we define the dot product that way. Okay. And then, so in particular, if 2 vectors are perpendicular, so if u is perpendicular to v, this implies that u dot v equals 0. This is fundamental. And that's because the cosine of 90 degrees is 0. Cosine of 0 degrees is 1, and so the dot product of 2 vectors going in the same direction is the product of their magnitudes. And if I missed anything else, does this pretty much summarize dot product? Okay. And then that brings us to the cross product. And cross product is more interesting and less important. Dot product is important in all dimensions. Cross product is mostly specific to dimension 3. It does generalize to higher dimensions, but we're not going to be talking about it, nor do most people. Now, cross product, there's a formula for it, right? And then it's if I do v dot w, cross product w, this does equal a vector, and this is the difference between the dot product and the cross product. Cross product, you multiply 2 vectors, and you get a vector out. Now, let me tell you what the answer is. It's v y w z minus v z w y. And if you can memorize that first one, okay, just memorize it, okay. Then the others are just sort of the cyclic rotations of it, meaning what I'm going to do is I'm going to put I'm memorizing the formula v minus v w, and then v w minus v w. And what I do is, see this y here? Advance it 1, it becomes z, right? Advance z1, it becomes x, because it goes, after x goes y, after y goes z, after z goes x. Okay, we're doing a cyclic progression, okay? And so after z comes x, after y comes z, and then I advance from here to here, I advance one more. After z comes x, after x comes y, after x comes y, and after z comes x. Okay, and that's the formula for the cross product. So if you can just memorize the first term, then you got them all. Okay? Now, where does this formula come from? Well, there's a really cool place where it comes from, but and I'm going to tell you what it is. But we can check already that I'll point out that v cross w, when you dot product it with v, that equals 0. And that's just an algebraic thing. Go ahead and, if you don't believe me, do it. Right? You'll get 0. You'll get 6 terms, right? Because v has components vx, vy, vz. So it's going to be this times vx plus that times vy plus that times vz. You notice there'll be 6 terms, and 3 of them have plus signs in front of them, and 3 of them minus signs in front of them. And then it turns out they all cancel. Yes?
That was a proof in the homework. Do you want us to do it in n dimensions? Or can we just do it with
3 dimensions. Because a cross product is defined differently in higher dimensions. You don't take the I don't remember the problem. It probably just has 3 dimensions, right?
Yeah, or it doesn't specify.
Oh, yeah, I think they mean 3 dimensions. Cross product. When you say the word cross product, it means 3 dimensions. Yeah. And you'll see why in our discussion here in just a second. That how it generalizes in higher dimensions is rather different. Okay. So, and by the way, that's also true for W. Okay, what that means then is that V cross product W is perpendicular to both V and W. So this is the usefulness of the cross product. So right there you can say, oh, this formula is really useful. I mean, given 2 vectors, it will give me another vector that's perpendicular to that too, which by the way, makes sense, right? I mean, can you all visualize that? Any 2 vectors going through the origin defines a plane. Let me just use your imaginations, right? That vector and that vector defines a plane spanned by these 2 vectors, right? And then I can say, well, give me a vector perpendicular to those 2 vectors, and in particular to that plane, right? And so given any 2 vectors, there's a unique sort of direction and the negative of that direction, right? That is perpendicular. So not only that up to a factor, this vector is the unique vector perpendicular to both V and W, assuming V and W are linearly independent. Now, V and W are the same vector, right? There's many planes that go through them, right? And therefore many normal vectors. Okay, from a practical standpoint, that's all you need to know about cross product. We could just end right there. I mean, there's one other formula, I guess, which is that the length of V cross W is equal to the length of V, length of W, times the sine of the angle between them. Okay? So I'll just draw the picture, I guess. So that's V, that's W, this angle is theta. That's kind of, let me see, try to draw a little better. Let's see here. Try to draw a plane here. That will be the origin, I guess. I don't know, that could be V, this could be W, and then the, I don't know, it's hard for me to draw. This is perpendicular to both of these guys, all right? So it's coming perpendicular to that plane spanned by V and W, and this is V cross W. And by the way, it obeys the right-hand rule. So if you use your left hand for the right-hand rule, it's not going to work. It's my first tip for you, right? But start with V and curl your fingers from V to W, less than 180 degrees, then your thumb is pointing in the direction of V cross W. The other thing you can do is take your first finger and point in the direction of V, your second finger, do like this, right? First finger in the direction of V, second finger in the direction of W. Make sure this angle here is less than 180 degrees. And then your thumb will be pointing in the direction of V cross W. It's called the right-hand rule. Okay? By the way, I cross J equals K. That's the convention. So when we're drawing X, Y, and Z coordinate axes, always make it to where the X-axis cross product, the Y-axis equals the Z-axis. It's just a convention. Now you could do it. You could look at the mirror image of that, and then you'd have I cross j equals negative k. But then you're going against convention. Okay, that's not how people. Now you might say, isn't it kind of arbitrary? Yes, it is arbitrary. We're going to say I cross j equals k. But it's once you accept that convention, then it just comes down to what your definition of the cross product is and so forth. So it's not that there's a right or a wrong answer. If you want all the formulas that everybody else uses to be correct, you use the same conventions that everyone else is using. Now, where does this come from? Let me just take it as an opportunity to tell you where this comes from. And that is, it comes from an interesting question. Let me show you all some math. Okay. Let's suppose. Actually, let me come over here to do this. This is the motivation for the cross product. Let's suppose that I'm in the xy plane. And I have a vector v here and a vector w. And let's suppose that I want to know what the area of that parallelogram is. Okay, so we'll call this A of v comma w. Okay. Actually, let me not put that in there. We'll just say the area of that parallelogram is A of v comma w. Okay. Now, what does that equal? That seems like a pretty reasonable geometry question, right? Well, there's a very interesting answer. Right? It turns out it equals the determinant of the 2 by 2 matrix for the first row is v and the second row is w. Whoa, where did that come from, right? Okay, so let me tell you why. This is really understanding what linearity means. Because this A of v comma w is linear in both slots, both the v and w slots. Okay. Now the first thing is we have to define area to be oriented area. So this A is not just area, it's oriented area. Okay. Now what does that mean? What we're going to do is we're going to say that this is I and that's j. We're going to say that this has area 1. So we're going to say that the area of I comma j equals 1. Okay. So now does anyone want to guess what area of I comma 5j equals? Well, that just means you're going to be 5 times higher, so I know you're all thinking it's 5, right? And that's the linearity property, right? We see that the 5 just factors out, right? Okay. But then that also means that what if I multiply instead of by the way, this I is not the square root of -1. We're using I and j as basis vectors for the two-dimensional plane. I is the vector 1, 0, j is 0, 1, and if you're in 3 dimensions, k is 0, 0, 1. Okay. But what if I put a minus j here, right? Well, if it's really going to be linear, this has to equal -1. Okay, so the point is, if my first vector is I, and my second vector is negative j here, right? Then I have to say that this right here has area -1. Okay? And that's just to get the linearity. You'll see how I have to do this if I want this notion of this area functional to be linear. You guys get this? So it's not that I want to do it, I have to do it, right? Okay. So, by the way, now you might say, wait a second, isn't this, if I just take this original one and I rotate it like this, isn't this picture the same as that picture? And of course it is, right? Except that you switch the order of the vectors, right? So if I rotate this, so in other words, this also equals, this -1 also equals the area of, this here. If I take this picture and rotate it, it's going to be +1, right? So this +1 also equals the area of j, comma, minus I. And so what it comes down to is that you have 1 is equal to the area of I comma j, minus 1 is equal to the area of, for example, I comma minus j. But let's see here. I also showed that a of j comma minus I is equal to 1, right? Because if we just rotate this, right, the I, yeah, I'm confusing myself. If I rotate this like this, the first vector becomes negative j. And then the second vector j becomes I. Okay, so, and then let's take this one here and rotate it up this way. Do you guys mind? Okay. So if this gives me minus 1, when I rotate, this one's not quite right. Okay, sorry. When I rotate this up, this negative 1, let's take this right here, which is this minus 1, and then the negative j becomes an I here, and the I here becomes j. And so if we want, this has area minus 1, we rotate it, it's obviously has area, oriented area should be the same thing as area up to a sign. So as I gradually rotate this, the area is either plus or minus 1 the whole time, but by continuity it needs to be minus 1 the whole time. And so this minus j becomes I, the I becomes j, and so we get a of j comma I is also equal to minus 1. Okay. So oriented area, in particular, one thing property it has is that a of, when you switch the vectors, as you have v and w over here, a of v comma w, when you switch the vectors, you get the negative. Okay, so that's one property this oriented area will have. Okay. And one thing you can see is, so if we define oriented area this way, when I equals oriented area. In other words, it's area with a sign. So in particular, it has this first property. When I multiply v by 5, then the 5 just factors out. And of course, that's true on the second slot as well. But then the other thing it has is that a of, here I'll do it in the second slot this time, w1 plus w2. This is a of vw1 plus a of vw2. Now, why is that? Well, imagine we have your first vector here is v, right? And then we have another vector here. This will be w1, and this vector here will be w2, w1, w2. And then when you add them up, of course, you get this vector here, right? Now, let me not draw in the parallelogram. It's confusing, right? Because y'all remember what the area of a parallelogram is. It actually is just the length, the base times the perpendicular height here. Okay, y'all remember that? So you just turn your head at an angle. This is your base, right? The area of this parallelogram is b times h. Fair enough? So in other words, it's the base times whatever the perpendicular height of w is, right? But the point is, you all see that the perpendicular height of w1 plus the perpendicular height of w2 is equal to the perpendicular height of w. I mean, if w equals w1 plus w2, perpendicular heights add. Right? And so, therefore, and the base is just the length of this v anyway the whole time. So b is not changing at all. All it's changing are the perpendicular heights. And so when I say, what's the area of v comma w1? Well, it's just the base times this perpendicular height. What's the area of v comma w2? Well, it's just the base times w2's perpendicular height. But the perpendicular height of w1 w2 gives you the perpendicular height of w1 plus w2. And so that shows that oriented area is linear. So you have this additive linearity and the multiplicative linearity. So this a is bilinear. Okay, so this the bottom line is that a of v comma w is bilinear. Just by the way, bilinear. Just like the dot product is bilinear. So then you might say, oh, it must be the dot product because they're both bilinear. But no, it turns out there's more ways to do bilinear things. In particular, the dot product, the order doesn't matter, right? v dot w equals w dot v. But here we already noted that this bilinear thing switches sign, right? When you switch the two vectors. And so, so now what's going on? Well, so let me show you a massive computation that we're always doing, okay? This is, okay, linearity is one of the most fundamental concepts in geometry and therefore mathematics, okay? So let me show you the massive computation we can do. We can say A of V comma W. I can now just write down a formula for it because it's linear, because it's bilinear. I can just write down the answer. Because this is A of Vx times the I vector, right? Plus Vy times the J vector. So everybody understand what I did? This V is Vx comma Vy, right? And so this is the 1, 0 vector, that's the 0, 1 vector, plus Wxi plus Wyj. And because it's bilinear, this equals 4 terms. All right, just think about it as like distributive law. We get this A of this, this, A of that, that, right? So I'll do it one step at a time. This right here is W, right? And now substitute in for, this right there is W, right? These whole things here. And so then plug that in, so I get A of Vxi comma Wxi plus A of Vxi comma Wyj plus A of Vyj. By the way, I do this once in public for you guys once a year, so pay attention. I'm not ever doing this again. All right, and by the way, and this is one of the problems of the subject is everyone hates doing what I'm doing right now, okay? But it's just kind of it's showing the linearity, okay? And I want to do it in its painful glory one time. You guys can see what I did? We got 4 terms. Massive bilinearity. Which equals, guess what? Remember the 5 factors out? Well, guess what? The Vx and the Vy's are like 5s, right? And so then we get Vx Wx times A of I comma I plus Vx Wy times A of I comma J plus Vy Wx times A of J comma I. What's a J? Plus Vy Wy A of J comma J. And what's the area? If you do the same vector twice, the area of the parallelogram is 0, right? And so what this all equals then is that's a 0, that's a 0. Area of I comma J, that is 1, and area of J comma I, that is minus 1. And so what we get then is Vx Wy minus Vy Wx. And then you're like, oh, isn't that just the determinant of Vx, Vy, Wx, Wy? Yes, it is. In fact, that's where the definition of determinant comes from. All right, that's why determinants are used all the time. Okay, this thing I'm calling area, I could have called it determinant. Okay, determinant of, if you show me a 2 by 2 matrix, its determinant is the area of the parallelogram spanned by row 1, row 2. Now you might say, oh, but that doesn't work for 3 by 3 matrices. Yes, it does. You can show me a 3 by 3 matrix. Look at row 1, look at row 2, look at row 3. That's 3 three-dimensional vectors. They span a parallelepiped. Like sort of like a cube, but skewed, right? It's sort of like a parallelogram, but in 3 dimensions. The volume of that parallelepiped is the determinant of that 3 by 3 matrix. Okay, so in other words, determinants are a geometric thing. Okay? So now, what has this got to do with the cross product? Now you recognize this term here, right? This term right here is in fact, this term right here is the third component of the cross product. So let's just finish the thought then. And I just want to, like, this is the type of thing I hate writing down. Like, people don't tend to like write it down, okay? But the point is, that y'all realize how simple this is. Because A of V comma W is bilinear, therefore, I know exactly what it is. It's that. Isn't that cool? Okay. So bilinearity, this is not just some random function of V and W. That could be incredibly complicated if it were. When something is multilinear, or then all of a sudden it becomes much simpler, right? So linear things are our friend. If it's not bilinear, I don't even want to talk about it. Think about even the dot product that I just erased. Or we're talking about the length of a vector. Length of a vector squared is Vx squared plus Vy squared plus Vz squared, right? That's not bilinear. That's not linear at all, right? Because you have squareds, right? But then that's why you invent the dot product. Because then the dot product is bilinear, and now we are off to the races. We can do computations and stuff, right? So when you see something that's not linear, you're like, is that related to something that's linear? Because I would much rather talk about things that are linear. Okay, so now let's go to 3 dimensions. And notice that x cross y cross equals z, using the right-hand rule. If I take 3 vectors, so given any 2 vectors, that gives me a parallelogram, right? And then you give me 2 and then I can make a cube out of them, right? Except it's not a cube, right? Notice it's easier for me to draw a cube, so I made the 3 vectors almost make a cube, but not quite, okay? So it's not quite a cube. It's a parallelepiped. And then if I define these vectors as u, v, and w, then I can say, okay, what's the volume of u, v, w? By the way, that's the determinant of the 3 by 3 matrix, where u is the first row, v is the second row, and w is u is the first row, v is the second row, w is the third row. Because there's really, I'm defining the determinant here as well. But I think it's better to think of it as the volume of the parallelepiped. Well, again, it's massively bilinear. And in fact, it's trilinear, right? Trilinear. It's linear in u, v, and w. And because it's trilinear, what you get is that it's a calculation just like this. Now, instead of having 2 times 2 equal 4 terms, there's going to be 3 times 3 times 3, which equals 27 terms. And I don't want to spend the rest of the class writing out 27 terms multiple times. You guys spare me? Okay. But here's the thing about it. You see which terms canceled? When you have a of jj, that's 0, right? When you repeat the j's or you repeat the i's, you're going to get 0, right? Same is true for a parallelepiped. Any 2 of them are the same. Like what's the area of I comma j? Well, that's going to be 0 because it has one of the dimensions collapsed. You guys get this? Mm-hmm. Okay. So what we're going to do is we're going to say so here's what we're going to have. 1 equals area of I, j, and k. And it turns out that whenever you switch any 2 of them, it changes the sign. And that's the same for the same reason as over here, right? So -1 is equal to the area of j comma I comma k. Okay? That's really the same thing we're talking about over here. Yes, question?
How are we taking the area of
Oh, not
3
area,
unit
volume.
vectors?
You got me. This is volume. And maybe I'll just call it V for volume here so I don't have to write VOL all the time, right? Thank you. So it's, you caught me there. So the volume of I comma j comma k will equal 1. And then -1 will be the volume of j comma I comma k. Does that answer your question? Thank you for the correction.
I just didn't know if you were doing something I hadn't seen
No,
before.
no, guys, I'm going too fast here. I'm going way too fast. That's all actually, I'm saying don't do your homework like I'm doing these lectures, right? Because I still need to go faster, right? Okay, so every time you switch 2 vectors, it changes by a sign. That's a rule we learned from over here. And so now let's go ahead and switch the I and the k, and now I'll change by a sign again and go back to 1. So this is volume of j comma k comma I. Now let's switch the first 2. We get volume of k comma j comma I. Now switch the last 2. We get volume of k comma I comma j. Now switch the first two, we'll get I comma k comma j. So these three equal -1, and the top three equal +1. And you can kind of see that if you cycle them, I, J, K, these are alphabetical on top. If it's alphabetical, then in terms of cycling, then it's +1. If it's reverse alphabetical, then it's -1. So a way to remember it. And then, and so you just say, okay, so in other words, these are the only 6 terms that aren't going to cancel. There'll be 27 terms, but only 6 that don't cancel. Because, by the way, how many different ways are there to permute I, J, and K? 3 times 2 times 1, 6. And those are all 6 of them. Okay. And so then what you get then is that you can write out the formula exactly. And what it equals is U sub x times V, Y, W, Z minus V, Z, W, X. Now, this for X, Y, Z, that's not surprising. It's going to be I, J, K, right? We know that's going to give us +1, right? This is going to be I, K, J. That's right here, I, K, J. That's going to give us -1, okay? And then there's, and then, plus, U, Y times, what are the terms involving U, Y? By the way, I'm cheating. I'm looking over here again. Okay. V, Z, W, X minus V, X, W, Z, I think is the answer. And again, you can see this is J. Is this going to be coming from the J, K, I term? J, K, I +1. And this will be J, I, K, which is right there. And that gives you -1, right? Okay. And then plus U, Z times V, X, W, Y minus V, Y, W, X. And again, K, I, J, that's right there. And K, J, I, that's right there, -1. And then now if you look at this, you're like, wait a second. This is a dot product of 2 vectors. It's the dot product of U, dot product V cross W, if we define V cross W that way. All right? I mean, y'all see that? If we take that definition, oh, this is just, it's just this, right? Now, in other words, what the cross product is, it's the definition that makes this a thing right here. Define the cross product so that this is always true. And then you sort of see how, this is obviously trilinear, right? Because you look at the definition of cross product, and you're like, okay, that's clearly bilinear. And then this is linear, dot product is bilinear. So this is linear in U, V, and W. Okay, so that's trilinear. This is trilinear. Guess what? It turns out that we need something that when you switch 2 vectors, it's antisymmetric. Now what's interesting is, you might say, well, wait a second, that's a little bit weird. Seems like U is special here, but it's not. It turns out this also equals, in case you're wondering, this also equals V dot product W cross product U, and it also equals W dot product U cross V. Okay? U, V, W, U, V, W, U. I have to keep it alphabetical, okay? Otherwise, I get a minus sign. Okay? And by the way, if I didn't keep it alphabetical, then I get a minus sign. Okay? Yes.
In your calculation for the volume, don't you cycle through with like a minus sign for the UY? Why is it plus 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 for the 3 terms?
Oh, because there's 3 other terms I didn't write down, and they would be minus, minus, minus.
Okay.
So, for example, if cross product has the property that if you switch it, it changes by a sign, right? So V cross W is equal to negative W cross V. And so in particular, if I to finish up right the other 3 terms, this also equals the negative U dot product W cross V, which equals negative V dot product U cross W, which equals negative W dot product V cross W, V cross U. Okay? And I'll leave that as exercises for you all to check. Okay? The only thing I proved was this thing in the box here, but in fact, the volume of UVW also equals the volume of VWU. It's just doing a rotation, right? And so if I look at volume of VWU, I get this equation. If I look at volume of WUV, I get this equation, right? And then if I say what's the volume of UWV, I switch these two, and then I get this equation, and so on. Yes.
Doesn't the volume given by the determinant generalize to higher dimensions? So what is the problem with cross products?
It does, right. And so if we say let's go to higher dimensions, what you realize is, so this is just a comment because we're not going to be using this in this class, but the reason it's kind of, I would call it, it's sort of, I hesitate to call it qualitatively different, but there is a pretty big difference. And that is that if we talk about hypervolume, okay, right, and then we need 4 vectors here. I'll use T, U, V, and W, okay? I can just say the alphabet in my head there. These are all vectors, right? If we try to do the same formula, we could say, well, it equals T dot product. But then we have 3 vectors here, not 2. So it's not going to be bilinear, it's a trilinear operation. And so we would have to invent some symbols or something, right?
But you could write the hypervolume as 4 different rows and the determinant, right?
Yeah. And in which case, everything will still go through. So if you so I'll tell you what is exactly the same. Okay. The notion of cross product is a little weird because if you think of it as 2 vectors out, it's the vector which is perpendicular. But when you go to 4 dimensions, there's a whole 2-dimensional plane that's perpendicular to any 2 vectors, right? And so you're getting a 2-plane out, not a vector out. Okay, so that's the main difference of cross product. But in terms of determinant, we can still think of this as the determinant of, okay, we're going to 4 dimensions instead of x, y, and z coordinates. We can use w, x, y, and z coordinates. But it gets annoying. Okay, what we do when we grow up is we number things, right? So it's T1, T2, T3, T4, and then this would be U1, U2, U3, U4, right? These are the coordinates. I was using x, y, and z before. And then this is V1, V2, V3, and V4. And then W1, W2, W3, and W4. And then we, to take the determinant, this will in fact equal, well, in principle, there's 4 times 4 times 4 times 4, which is 256 terms. But most of them are zeros. And the only ones that aren't zero, remember before, down here we got 2, that was 2 factorial. Here there's 3 as 3 factorial. 4 factorial is 24. There will be 24 terms, and that's the determinant. And it's the usual formula. It's going to be, for example, it's going to be T1 times the determinant of, this submatrix here, right? And then so on, right? And so that's where those formulas come from. It's completely derivable from the fact that the determinant is quadlinear. In this case, it's we just say multilinear. Once you get above 2, you just say multilinear, right? So this is multilinear, linear in all 4 slots. And then from that, you can just write down the formula, essentially. Any questions? Okay, so enough about that. Let's get into, I think it's good to understand where these things come from. I appreciate that. I hope you do too. Okay, so then that brings us to these Frenet formulas. Trying to understand a curve in R3 now that we have a solid sort of background on this stuff. And so these Frenet formulas are just a way of understanding curves. Sort of a introduction to geometry in 3 dimensions. And so suppose that we have a curve in 3 dimensions. There's your curve. At any given point, we have Let's talk about a curve parameterized with speed 1, beta of s. At any one given point, we have the tangent direction of the curve. We call it t, and that equals beta prime of s. And then what we can do is, you remember last time where there's this trick, right? Remember that 1 is equal to beta prime of s dot product beta prime of s, right? Because why? The length of beta prime of s is 1 because it's a curve parameterized by arc length. So you take DDS of both sides, and then you get 0 is equal to 2 beta prime of s dot product beta double prime of s. And so what you see that is that beta double prime of s is perpendicular to beta double prime. Okay, so in other words, if I look at beta double prime, it's going to be some vector like this. And it will be exactly perpendicular. We're in three-dimensional space here, but it'll be exactly perpendicular to beta prime of s. Does everybody understand? And yes.
So is
Let me make it obviously longer, so you don't think it's the same length or anything. Okay? It could be quite a bit longer. Yeah. Question?
and beta double prime of s is basically saying like as beta prime changes, like that's mapping the direction of where those individual.
Yeah, it totally makes sense, right? Let me see if I can. If I'm walking at constant speed, right? I'm going this way, right? If I'm curving to the left, right? That's beta double. When beta, then the rate of change in my direction is that way, right? It's perpendicular to my motion. If we talk about, okay, he's curving to the left, now he's curving to the right. Well, left is that way, right is that way, right? The rate of change in my velocity vector is perpendicular to my motion, as long as my velocity is constant. So that should be relatively intuitive. I mean, you can think of it as the vector was this, now it's that. It had been this, right? So you can see that's sort of the delta, right? You can see it's sort of changing, and it's exactly perpendicular is what this calculation shows. Yes.
In 3D, there's a whole plane that is perpendicular to beta prime s. So how do we know beta double prime is?
Yeah, we still don't know. It's just one. It's one of those perpendicular directions. Yeah. And so, so let's make it some notation established. T is the tangent vector, so it's t of s if you like. And then at any given point, that has length 1. Okay. And then it becomes handy to go ahead and say, let's let this have length 1, and let's let this normal vector here be n. And what is n? N for normal, by the way, I think, right? So it's perpendicular to t, normal to t, and so we say, well, look, this is just going to be beta double prime of s divided by its length, which we call kappa, by the way. Remember that? So this is beta prime of s, and we're going to define kappa here equal the length of beta double prime of s. That's what we did last time. So when we divide beta double prime of s divided by kappa, its length, then we get a unit vector n. By the way, it's a general thing. If you have a vector of length 5, you divide by 5, now it has length 1. So in general, if I want to take a vector and give it length 1, I just divide it by its own length. Okay? And then there's something called the Frenet frame, which is you define one more vector. This is called, I think, the binormal vector b, and this is equal to, I think it's t cross n. Make sure I got those in the right order. Yeah, b equals t cross n. And now these three vectors put together, t, n, and b, and they all vary as a function of s, are called the Frenet frame. And this is an orthonormal. So what is a frame? It's an orthonormal set of vectors at every point. So we have, in dimensions 3, we need 3 vectors that are mutually perpendicular. It's kind of like I, j, and k. I, j, and k are a frame. And it just turns out what we're going to do is understand things in terms of t, n, and b. Okay? And yes,
Sorry.
question?
So B is orthogonal to both t and n.
Mhm.
Is it also a unit vector?
Yes.
Okay.
And the reason is that these vectors have length 1 and are also perpendicular to each other. And so we can use our properties of cross product, but I didn't erase it, which is that the length of the cross product is the length of the two vectors times the sine of the angle between them, and they're 90 degrees apart. Sine of 90 is 1, so you get 1 times 1 times 1. Yep. Good question. Okay, so this gives us our Frenet formulas. And what they're about is how this frame is changing. What is T prime of S? What is N prime of S? And what is B prime of S? And it's quite nice. Now T prime of S, just look at our formula here. T was beta prime of S. So T prime of S is just beta double prime, right? And beta double prime is just equal to K times N, right? And so it turns out, so it's just K times N here. Now what we're going to do is we're going to say it's so much times T plus so much times the second vector N plus so much times B, okay? And we're going to fill in these gaps here, okay? Now, you might say, why am I doing this? Well, it's sort of like I, J, and K, right? You can always express any three-dimensional vector as a sum of so many I plus so many J plus so many K, right? And we're going to do the same thing. We're going to do it with T, N, and B. In fact, let me just review some very basic linear algebra, which is, you guys all know that 3, 4, 5, right, is equal to 3I plus 4J plus 5K, right? That's just notation, right? But another way to write that is that this vector, which we'll call 3, 4, 5, is equal to V dot I, which is 3, right, times I. You guys agree? And then that when I take I, which is 1, 0, 0, and dot product with 3, 4, 5, I get 3, right? So how do I compute that 3? It's just 3, 4, 5 dot product 1, 0, 0, right? And that's the coefficient for that 3. And so in other words, this is actually a more general formula for how we do this. I didn't draw all the arrows over the I, J's, and K's. I left them off with their vectors. And it turns out that's not just true for I, J, and K. It's true for any orthonormal frame. Okay. Now you might say, how do you prove that? Well, let me just prove it for I, J, and K real quick, okay? Do you mind? And then it turns out the same proof for everybody else. Okay, so I could say conjecture. I think this is true. Well, okay, well, dot product both sides of the equation by I. If I dot product both sides of the equation by I get V dot product I on the left. And what I get here is, I get a 1, 0, 0, right? So I get V dot product I on the right, check, right? So if I dot product both sides by I, it works out. If I dot product both sides by J, it works out also. And this is using the orthogonality of I, J, and K. If I dot product both sides with K, it works out. And in some sense, we're verifying that these vector equations are true in all 3 dimensions. And therefore, it's true. Okay, so anyway, this is a general fact. Okay, and so the point is that when I have a T prime of S or an N prime of S or a B prime of S, I can express them as linear combinations of not only I, J, and K, but what we want to do, T, N, and B. We're trying to understand the geometry of these curves. Who cares what I, J, and K is? We care about quantities that actually relate to the sort of the physics of the curve, right? If I'm flying around in an airplane, last thing I care about is what someone else calls the x-axis. I care about what direction am I going, what direction am I curving, right? What's sort of the geometry relating to my curve. Okay, and so now what we want to do is fill in all these curves. And here's one thing that you can do right off the bat. Remember this trick right here? We're going to use this trick again. This is the trick we're going to use 17 times in this course. Because 1 also equals T of S. Well, let me not do T of S. I'll do B of S because it doesn't matter. Okay, B of S dot product B of S. Now take dot product of derivative of both sides. You get 0 equals 2 B prime of S dot product B of S, right? But that means that B prime of S is perpendicular to B of S. And so what's the general principle? If I have a constant length curve, in this case a unit length curve, then this rate of change will always be perpendicular to itself. Okay? So in particular, what is this coefficient right here? Well, this coefficient here is in fact just B prime of S dot B, but I know that's 0, so this term here is 0. Right? The rate of change of a unit vector is always perpendicular to that unit vector. And so that means N prime of S dot N would be 0, and then T prime of S dot T would be 0. So we have zeros along the diagonal. volume. So actually, I can just erase these terms. There's 0. Okay, cool. Now there's another principle. And it's kind of this trick slightly improved, right? And what this trick is, you guys ready? Is that I know that I also know that 0 is equal to n of s dot product b of s. Fair enough? That's just saying they're perpendicular. Right? No matter, now they're changing all the time, but their dot product is always 0 because they're perpendicular. So now take ddf of both sides, and I get 0 is equal to n prime of s dot b of s plus n of s dot product b prime of s. But wait a second, n prime of s dot b, that's this term right here, right? And b prime of s dot n, that's this term right here. And they have to add up to 0. Okay, so this is like the full power of the trick. So in other words, these terms add up to 0. So in other words, this thing is anti-symmetric. These coefficients, if you think it was a 3 by 3 matrix where I drew the underscores, right? This is an anti-symmetric set of coefficients. Okay, so it's anti-symmetric. Anti-symmetric. By the way, which explains why you had zeros along the diagonal, because all anti-symmetric matrices have zeros along the diagonal. Anti-symmetric, because when you flip it, you flip to yourself, and you have to be the negative of yourself, and 0 is the only number that equals the negative of itself. Okay, so it's anti-symmetric. Okay, so now let's start filling in these numbers. Remember, t prime of s is just, t was beta prime of s. T prime of s, therefore, is beta double prime of s, which is just k times n. So we know this right here is a kappa, which, by the way, means this is negative kappa, right? By the way, it's just kappa times n, so that's a 0 here, which means we also have a 0 here. Anti-symmetric. Okay. So once we say that this is just the rate of change of t is, which is beta prime of s, is there, the rate of change of t is therefore beta double prime of s, which is k times n entirely. If this is k times n, we already know we had a 0 there. We also get a 0 here. By the way, I keep on saying k. That's kappa. This is kappa. That's minus kappa. If that's 0, this is minus 0, which is 0. This picture is simplifying quite a bit, isn't it? We only have 2 slots left, and we know that they're negatives of each other. And so, gee, how do we compute it? You don't. You don't. We define this to be the torsion tau, and then by definition, this is negative tau. Okay? And these are the Frenet formulas. And so what we have done is we introduced a definition that everything else that we already had, which is what tau is. Tau here is simply what you get when you look at n prime of s and then dot product it with b of s. By definition, it's a definition. And we see it also equals the negative of n of s dot product b prime of s. Okay? By the way, what I wrote down right here is just this identity here, right? So you want to get really, really good at, memorize this. Okay, this trick here, these tricks, get really expert at them, right? We're like, it's almost like integrating by parts, but not quite, right? But anyway, memorize that if I have 2 unit vectors dot product, point is their dot product is 0, right? So if I take a derivative of it, right? Then this is equal to that, because sometimes you'll be computing something like, oh, I have no idea what that is, but I can compute this, right? So this is an important trick for your homework and so on. Okay, now what is all of this? Okay, I mean, so what we see is there's 2 quantities, this kappa and this tau. Those are the 2 quantities that define the rate of change of your Frenet frame. Okay, and if we kind of summarize what all the formulas are, that's the definition of torsion. Kappa here was just the length of you know, beta, I guess, beta double prime of S, right? Let's see here. If I wanted to express the torsion in terms of beta, right? What would that be? Okay, well that's an exercise. There's a formula that we'll work out at some point. But it's just going to be, I guess let's just write it out. It's going to be negative, what's n of s? N of s is right here, right? That's beta double prime of s divided by the length of beta double prime of s, right? And then dot product. That's what n is. And then you know what I'm going to do is I'll use this formula over here. It's just a little bit easier, okay? Equals. Okay. So what I have in parentheses there is, in fact, n of s, I think, right? And then we can take dds of that, put a prime there, and then we can dot product it with what b of s is. But b of s, we defined it, where we define it right here, it's just t cross n. What is t? It's beta prime of s. And then what's n? We have it right there, right? It's beta double prime over the length of beta double prime of s. So what I'm pointing out here is that all this stuff is computable in terms of your curve, right? So given a curve, you can use these formulas to compute what your Frenet frame formula is. But then what we have are geometric quantities. The geometric quantities are kappa and tau. So what do they tell us? What do kappa and tau tell us? Well, I mean, there's the formulas for them, right? This is what kappa and tau are, but what does it mean geometrically, right? Well, we already know what kappa means. It's the curvature, right? It's theta prime of s generalized to 3 dimensions, right? It's the rate of change of your direction. If you're on a circle of radius r, the curvature is 1 over r. Okay. And by the way, everything is a circle of radius r up to second order. See, this kappa only depends on second derivatives, right? So if someone has a curve here, I would simply come to this point. I would look at the plane defined by t and n. I would then inscribe a circle that matches it as well as possible, matches it to second order. And I would say the curvature is the 1 over the radius of that circle. They call it the osculating circle, by the way. And the plane defined by t and n, they call that the osculating plane, right? At any given point, t and n define a plane, and it's sort of moving through space, right? Think about you're flying an airplane, right? There's the direction you're going. There's the direction you're turning. That defines a plane. Now, there is a problem with this whole setup, by the way, and that is, what if kappa is 0? Kappa is the length of beta double prime of s. You get 0 over 0 in that case, right? So what if you're not turning at all? You're just going straight. None of this works. Okay, so this only works if you're turning, if kappa is non-zero. So in all this discussion, we have to assume kappa is already positive, is already not equal to 0. So it's already greater than or equal to 0, but we have to assume it's not 0, okay? So all this works as long as you are, in fact, curving. Okay, you can't be going in a straight line because then n is not defined. If n is not defined, then b is not defined, right? And so this whole all breaks down. But what does tau represent? Okay, what does tau represent? Yes.
Wait, shouldn't that be the cross product, not a dot product?
Thank you.
But
The second one.
Yeah.
Thank you. Thank you very much. Appreciate that. You're a hero. I'm very disappointed if I get there late. If everyone leaves and I'm thinking, "Oh, this is so great," and I see my mistake. Oh. Yeah, absolutely, cross product. Thank you for catching that. Because B is a cross product of things, right? Okay, so what is tau? It's called the torsion, and we can see it right. I think we can see it best from this formula, actually. It's the rate of change of B, right? The binormal. Now, what is the binormal B? remember that oscillating plane is, the plane that we're in, right? The plane that we're curving in, right? T and N define a plane. Well, planes are characterized by their normal vector. That normal vector is B, right? B is defining the plane that you're in, right? And if you're in a plane and you never change, like you stay in the same plane the whole time, then your B will be the normal vector to that plane, right? So if I'm a fly flying in this room, but I stay in the plane x plus y plus z equals 7, right? Then my binormal vector will simply be 1, 1 divided by the square root of 3. It'll be the vector perpendicular to that plane. And it won't change, and since the binormal vector is not changing, this will be 0, and you have 0 torsion. So if you stay in a plane, then your torsion is 0. But as you change, it's your oscillating plane, right? Is the plane that you're in defined by the direction you're going and your curvature, right? I'm going this way, but I'm curving that way, right? That defines a plane. And as that plane changes, then I get torsion. So torsion is a measure of how the plane that I'm flying in is changing. Okay. There are some things in the book you show that if you have 0 torsion, you must be stuck in a plane. You'll be in one plane the whole time. It's true. There's some proofs. Proves the short distance between 2 points is a straight line. Okay. Refer you to the book for that. Let's see. What's another good one? Examples. The simplest example of what's an example where we have curvature but no torsion? That would be a circle. A fly just going around in a circle, right? Same plane the whole time. What would be the simplest example where you have curvature, where you have non-zero? Let's go ahead and take constant curvature and also constant torsion. That would be a spiral. You're spiraling down, right? You see, you're not staying in the same plane. A circle is in the same plane. A spiral is not in the same plane. You guys know who John F. Kennedy was, obviously? Do you all know of his son, JFK Jr.? He's outside. He used to be the most eligible man, and he was considered the most eligible bachelor in America at one point. John F. Kennedy Jr. John F. Kennedy's son, right? He was anyway, he was a celebrity. You guys don't know him, though. It's very interesting how quickly they will forget you when you fly your airplane in a spiral right into the ocean and die. He was a pilot, and he was not rated to fly at night, and he flew at night anyway, and he was out over the ocean, and he got into a spiral, a downward spiral, and he was not instrument rated. His instruments told him he was in a downward spiral, but he did not believe it. And that's the common mistake that pilots make, is that they have constant curvature and constant torsion, and they're just spiraling straight down into the ocean. And the altimeter says they're going down, but it seems like you're flying flat and level to them, right? And it so happens it's possible to choose K and T, and K and tau just right, so that when you bank your airplane, that changes which way it seems down to you, right? But also when you're in a circle, that changes. There's a centripetal acceleration that pushes you in another way as well, and you can balance those things out to where down seems straight to the floor. And so he had a constant K, constant T curve at night where he couldn't see anything, and it seemed like he was flying straight and level. Force of gravity was straight down for him. His instruments were saying that he was spiraling down and he was banking, which he was, and unfortunately he and his two passengers died, of course, on impact. And all that could have been avoided if he had taken this class. Yeah. Anyway, so yeah, a spiral would be the simplest example of constant K and constant T. Yes.
In the equals for B of S,
Yep.
how is this not now a scalar?
Where are you?
Where it says B of S equals like downwards diagonal to the B double prime of S.
I'm not seeing where you are.
Oh, the bottom right of the middle board.
Bottom right here.
Yes.
Okay.
Is that not a scalar because it's a dot product?
Yes, and that's what tau here is a scalar. Yep.
Oh,
Tau and kappa are both scalars. Yeah, so the vectors here, let me put the vectors in, are the T, N, and B. And then the tau and kappas are just scalar factors in front of the vector.
So you're saying the tau equals that, not B of S equals that?
That's right, yeah.
Okay.
Tau equals this, yep. All right, so you guys, good luck with the homework. And there's more stuff on the videos if you want more discussion on this.